Good morning, ladies and gentlemen, and welcome to the third time that I'm attempting to film this video. Hopefully no mishaps happen this time. So anyway, we're going to discuss today how to run a one-sample t-test. Now, the term one-sample t-test refers to the fact that we're running a hypothesis test involving one sample mean. Right? This is different than a one proportion z-test, which was when we ran a hypothesis test involving one sample proportion. Okay, so that's what we're doing. We're running one sample t-test, and we're going to use the data that I collected this weekend. So I have this hypothesis that on average, my AP Stats students own more than 7 pairs of shoes on average. So what I'm going to do is take an SRS, a simple random sample of 8 of my students, and then we're going to test this hypothesis. So I don't have the data yet. You're going to see me choose the 8 random students, and we'll use that data to test my hypothesis. Now, first, let's just set some things up. The plan, my parameter of interest is mu, and I'm going to let mu be the average number of shoes owned by my students this year. All right, so that's talking about you as the population, AP Stats students. The null hypothesis is that mu will equal 7, and the alternative will be my claim that mu is greater than 7. Okay, so if I'm claiming greater than 7, then the null is just going to be equal to. The null will always be equal to some sort of equality, whereas the alternative is going to be some sort of inequality. All right. We're going to get a little crazy today. We're going to use an alpha value of 0.08. And again, as I mentioned in the description of the problem, we're going to have a sample size of 8, which means that our degrees of freedom will be 7. So that's an important thing to know, is that our degrees of freedom is 7. Remember, as the degrees of freedom changes, then the t distribution also sort of kind of transforms along with the degrees of freedom. And as mentioned before, we're going to perform a one sample t-test. All right, let's go ahead and look at the population. So this right here is the data that you sent me. I'm just looking at the question that asked, how many pairs of shoes do you own? And I've assigned each student an identifier, so a number from 1 through, a unique number from 1 through 98. Only 98 responded out of, I believe, what is it, like 104, so not terrible, actually, pretty good. And in the second column here, this is the actual responses to that question, how many pairs of shoes do you own? So interesting, some of you own a lot of shoes, I have to say. I was kind of shocked by this, but that's fine. All right, here we go. Let's collect the data. So our good friend, random.org, I know you've missed it. What we're going to use it to generate a sequence of numbers, smallest value, a sequence of unique numbers, smallest value of 1, largest value of 98. And we're going to choose the first 8 numbers in that sequence. So let's get the sequence, and here we go. So let's choose the first 8. All right, and that's my sample. That is my simple random sample. And I'm going to plug those numbers in to this column L here. These are the random numbers. So these are basically the 8 random students. And on the right, I had a formula set up to look up the number of shoes that each one of those students owned. So this is actually the information we're interested in. These are the numbers that represent the shoes. All right, so let's write those numbers down. So we have 6, 2, 4, 12, 6, 6, 2, 4, 12, 6, and 14, 5, and 2. Very interesting distribution of number of shoes owned. All right, so I'm going to take those numbers, and I want to know the observed statistic, which is X bar. So what's the average of this sample? I'm also going to find the standard deviation of this sample, as we're going to need it to approximate the standard deviation of the population. So I'm going to enter the data into my list 1, 6, 2, 4, 12, 6, 14, 5, 2. Those are my 8 numbers. I'm going to go to stat calc 1 var stats on list 1, and I find that X bar is 6.375, and my sample standard deviation is 4.4058. And right off the bat, you can see that my alternative hypothesis is really not looking good based off of this sample. But we're going to proceed because I just want to show you how to run the test from beginning to end. All right. And there's nothing we can do about the data that we collected. It is what it is. I'm not going to change my hypothesis based on what I chose. I'm just going to carry through. All right, let's justify. So the 3 conditions are the random sample, the 10% condition, and the nearly normal condition. The only one that should not sound familiar is the nearly normal condition. Well, it is something that we have seen in the past, but not recently. So random sample, okay, you just saw me choose a random sample using our good friend random.org. Okay, so that's good. The 10% condition, 8 is definitely less than 10% of all my AP Stats students, so we're good there. The nearly normal condition, you ask yourself 2 questions. First, is n greater than 30? If so, then you're good to go. You're done. The nearly normal condition is checked off. However, in this case, it is not. And so we have to ask ourselves the second question, and that is the sample nearly normal? Now, what the heck does that mean? Well, if we take the data that I just collected and place it in a normal probability plot, does that normal probability plot indicate that that sample is distributed normally? So we're going to check the normal probability plot. You might recall the normal probability plot is a data display that we learned about months and months and months ago. And the idea is if the normal probability plot looks linear, then that data can be assumed to be nearly normal. So we're going to check the normal probability plot. We're going to hope to see a line. So I'm going to take that data in list 1, and I'm going to go to second stat plot, and I'm going to choose the very last display. That very last display in stat plot, that's your normal probability plot. Zoom 9. And in this case, the normal probability plot is, look, it's never going to be perfectly linear, but it's not too bad. Hopefully you're following along and you're checking on your own calculator, but I'll try to draw it. Again, it's not perfectly linear, but we have something that kind of looks like this. Right, I know we have like some gaps and we have some verticals going on there, but ultimately, if we zoom way out, we have something that is not too bad in terms of linearity. So what I'm going to say is that the normal probability plot is nearly linear. Therefore, the sample is nearly normal. Now, if you get something that's just crazy, obviously not linear, then you would obviously just proceed with caution. Or in practice, if you got something that wasn't linear and the nearly normal condition just wasn't met, then you'd have to figure out some other way to analyze the situation. But for now, I obviously just want to show you this process. So we're gonna continue no matter what. But in this case, I think we can say that the normal probability plot is nearly linear. All right, moving on. since all the conditions are met, we now have an idea of what our sampling distribution will look like. It'll be distributed using the t-distribution, centered at my assumption, which is that mu is equal to 7. And it will have a standard error of sigma x over radical n. I don't know sigma x, that's the population standard deviation, but what I do have is the sample standard deviation, and that'll be a stand-in. So 4.4058 divided by radical 8, which is the sample size. And plugging this into a calculator, I get 1.5577. All right. By the way, I just want to add some context. This X bar, 6.375, this represents pairs of shoes, or I'm just going to say shoes, but hopefully you understand that I mean pairs of shoes. All right, now we're going to use this distribution and the observed sample to calculate the t-test statistic. So I'm going to take my observed, which is 6.375, minus the mu, or the assumed mu, and I'm going to divide by standard error, which is 1.5577. And this test stat is approximately equal to negative 0.4012. All right, so remember this, what this tells me is that my observed statistic is 0.4012 standard deviations below the hypothesized mean. And so just to give you a sense for when we calculate our p-value, we're gonna end up getting a pretty large p-value because, well, what am I, my center is assumed to be 7. This is my distribution of X bar. I have an observed stat that is below the mean. Here's my observed X bar. But the thing is, my assumption is that mu is greater than 7. So when I calculate my p-value, I actually have to shade to the right. So you can see it right away. We're going to get a large p-value. Let's do that right now. The p-value is the probability that t is greater than negative 0.4012. Right? Again, greater than only because that's my alternative hypothesis. My test statistic is below the mean, but I'm still doing greater than because of my alternative hypothesis. And we're going to calculate this by using a function called TCDF. And I don't know that everyone has it. If you do not have TCDF, use the T table. So you're going to use TCDF. And I'll show you what to input, or you're going to use the T table. So for TCDF, you enter the lower bound in terms of a t-test statistic. You enter the upper bound in terms of a t-test stat, and you enter your degrees of freedom. All right. So in this particular case, my lower bound is, let me go to second distribution, TCDF. My lower bound is actually the test stat of negative 0.4012. My upper bound is just some very large, absurdly large number, which is like 9999999. And my degrees of freedom, of course, are 7. And this leads to a p-value. Let me get that arrow out of the way. This leads to a p-value of 0.6499. Okay. So there we have it. Please, please, please use your calculator to try to find, or the t-table to try to find this p-value. All right, let's go to the summary. Well, first, the interpretation of this p-value. So if the true average number of shoes owned by my AP Stat students is 7. So basically I'm saying if H null is true, then the probability of observing a sample average of, what did I observe? What was my X bar? 6.375. Shoes or more, and again, the or more is because my alternative hypothesis is greater than, and that probability is 0.6499. And now, so that's the interpretation of the p-value. Now let's make a decision on the hypotheses. Well, since 0.6499 is greater than 0.08, which was our alpha, we are going to fail to reject H null. Right, so what we've done here is we've gotten a situation where it's pretty clear that we don't have evidence for the alternative. So all we can say is we failed to reject my initial null hypothesis, which is that mu equals 7. All right. Now, if you think this data maybe sheds evidence on some other claim, then you'd have to test that other claim separately. Maybe you want to test a new hypothesis that says mu is less than 7. And if that's the case, you can certainly do that. But we can't make any other claims besides what this specific hypothesis test is telling us. All right, so we failed to reject the null hypothesis, and therefore we do not have evidence to support the claim that my Bronx Science students own more than 7 pairs of shoes on average. Okay, and there you have it. So according to that sample, y'all do not own more than 7 pairs of shoes on average. And if this hypothesis test is wrong, then maybe I've made an error, and what type of error might that be? I'd like you to think about that. All right, folks, so hopefully that made it clear how to actually go through each and every step to run a one sample t-test. I will be available on SGI again every single day this week. So please ask questions if you have any, or just simply post something on Google Classroom or something like that. But until next time, ladies and gentlemen, have a great day.